Welcome back, everybody. My name is Keith Wiggins with PAG Waste Management. We're going through the Handbook of Biomass Downdraft Gasifier Engine Systems. We're on Chapter 3, and this has been a pretty good read so far. Let's keep going. Chapter 3 is Gasifier Fuels. Here's the intro. Biomass fuels occur in a multitude of physical forms. The often heard manufacturers claim that a particular gasifier can gasify any biomass fuel is a naive statement, and each form can be expected to have unique problems until proven otherwise. This physical disparity accounts in part for the large number of gasifier designs available today. The gasifiers used widely during World War II used specially prepared 1 by 2 by 2 centimeter cubed hardwood blocks. However, such blocks could represent only a tiny fraction of the biomass materials available for gasification. Some gasifiers currently are undergoing design evolutions that will enable them to use a wider range of fuels. Nevertheless, fuel properties are very important in determining satisfactory operating conditions. Therefore, these multi-feedstock gasifiers will be able to use only a limited range of biomass with controlled specifications, and anyone installing such a gasifier should have tests run on the fuel to be used before deciding upon a purchase. The ability to specify fuel parameters is very important, and we discuss them in this chapter. Fortunately, a wide variety of tests are available for biomass and charcoal gasifiers that can be useful in those interested in gasification. Green wood can contain up to 50% water by weight, so its properties vary widely with moisture content. The chemical compositions of biomass, expressed on a dry, ash-free basis, is more constant than that of the various coals like bituminous, anthracite, lignite, as shown in figure 3.1. Here we go, figure 3.1. Furthermore, more than 80% of the biomass is volatile. Coal is typically only 20% volatile. The remaining 80% is unreactive coke, which is more difficult to gasify than charcoal. Biomass generally has very low sulfur and ash content compared to coal. However, unlike coal, biomass comes in a wide variety of physical forms, making it necessary to tailor the shapes of the gasifier. Fuel drying equipment, feed systems, and ash removal equipment to each form. Therefore, the resulting gasifier design must be very fuel specific. Biomass fuel analysis. Proximate and ultimate analysis. Two types of analysis, proximate and ultimate, are useful for determining the physical, chemical, and fuel properties of a particular biomass feedstock. These analyses were typically developed for coal and are widely available from commercial laboratories. They are described in detail in the publications of the American Society for Testing Materials, shown in Table 3.1, and we'll see that in a second. The equipment necessary for performing elemental analysis is shown in Table 3.2. The proximate analysis is relatively simple and can be performed with a drying oven, a laboratory furnace, and a balance. The ultimate analysis involves more advanced chemical techniques. Both analyses can be performed in commercial laboratories for $25 to $100 in 1988 funds, so I don't know, $500 now. The proximate analysis determines the moisture, volatile matter, ash, and, by difference, fixed carbon content of a fuel using standard ASTM tests. Moisture is analyzed by the weight loss observed at 110 degrees centigrade. The volatile matter is driven off in a closed crucible by slow heating to 950 degrees centigrade, and the sample is weighed again. The high heating rates encountered with an actual gasifier yield a higher volatile content and a lower fixed carbon content than the slow rate used in the ASTM measurement, but char yield from the gasifier is expected to be proportional to char yield from ASTM levels. The proximate analysis for selected biomass feedstocks and other solids are shown in Table 3.3, next page. Note that more than 70% of the biomass material is volatile under the conditions of the test. The proximate analysis generally includes moisture content measured on a wet basis, MCW, and then we have a formula, 3.1, MCW is equal to the wet weight minus the dry weight, and enclosed divided by the dry weight. So sometimes moisture content is reported on a dry weight basis, MCD, where MCD is equal to the wet weight minus the dry weight divided by the dry weight. Did I read that right? Those are both the exact same formulas. Wet weight minus the dry weight in parentheses. Oh, right. So denominator in MCW is wet weight, and denominator in MCD is the dry weight, obviously. Okay. So if we look at 3.3, we can see volatile matter, fixed carbon, ash, and there's a reference down here for the different items. Interesting. Moisture contents for typical biomass fuels are shown in Table 3.4. The effect of moisture content on heat recovery and combustion efficiency is shown in Table 3.5. We'll see both of those later on. Recoverable heat drops dramatically with increased moisture since the heat of vaporization of the water is not normally recovered during combustion. Since biomass varies in its properties from day to day and from load to load, it is common to report analysis on a dry basis and sometimes on a moisture and ash-free basis. It is then a simple matter to calculate other specific conditions from this value. The ultimate analysis gives the chemical composition and the higher heating value of the fuels. The chemical analysis usually lists the carbon, hydrogen, oxygen, nitrogen, sulfur, and ash content of the dry fuel on a weight percentage basis. Ultimate analysis for a number of biomass and other solid fuels are given in the Table 3.6 for various chars in Table 3.7. So we'll look at those later. In Table 3. Note that in Table 3.6 that biomass is typically very low in both nitrogen and sulfur content relative to fossil fuels. However, selected biomass feedstocks may have much higher values. The sulfur and nitrogen contents of selected biomass fuels are shown in Table 3.8 and 3.9. So we got a bunch of tables to go through in the future here. But in Table 3.2, the wet-dry basis moisture content comparison. Okay. The ash content of biomass is typically much less than that of coals, but some forms have a high ash content as shown in Table 3.3. This can lead to ash melting, known as slagging, which can cause severe problems in some gasifiers. A standard ASTM method is available for measuring the slagging temperatures for ash. That's Table 3.1. Oh, that's interesting back here. Huh. Test numbers. Okay. The higher heating value of the fuel is determined by reacting the fuel with oxygen in a bomb calorimeter and measuring the heat released to known quantity of water. The heat released during this procedure represents the maximum amount of energy that can be obtained from combusting the fuel and is a necessary value for calculating the efficiency of gasification. The high heating value, HHV, is measured in this test since liquid water is produced. However, the low heating value, LHV, is more relevant to the amount of energy produced, and this can be calculated from the HHV value shown in Table 4.1. So you can intuit one value from the next. The heat of combustion is determined by composition of the biomass, and in fact can be calculated with considerable accuracy. Let's see here. So it has formulas again for HHV, and that's a little bit complex. We'll leave that. Where the C, carbon, hydrogen, sulfur, ash, and oxygen, and nitrogen are the weight percentage of carbon, hydrogen, sulfur, ash, oxygen, and nitrogen in the fuel. The calculated values agree with the measured values with an absolute error of 2.1% for a large number of biomass materials. For physical tests, one of the most important physical characteristics of biomass fuel is the bulk density. The bulk density is the weight of biomass packed loosely in a container divided by the volume occupied. Clearly, it is not an exact number depending on the exact packing of the particles. The fuel shape feeding characteristics determine whether it would be feasible to simply use gravity feeding techniques or whether assistance such as stirring and shaking will be required. The angle of repose for a particular fuel type is generally measured by filling a large tube with the fuel and then lifting the tube and allowing the fuel to form a pile. The angle of repose is the angle from the horizontal to the sides of the pile, like the triangle angle. The basic feed characteristic is more easily judged from dugout angle of repose, the steepest angle measured from the horizontal formed by the sides of the pile of fuel when a material is removed from the bottom of the pile. Angles approaching or exceeding 90 degrees are a good indication of the tendency of the fuel to bridge or tunnel in the gasifier. Other fuel parameters. The tests and analysis just mentioned are in widespread use because they were developed for use in other industries. However, many other tests need to be developed specifically for the gasification processes. This section addresses the effects of other fuel parameters on biomass gasification, illustrating the need for more specific testing procedures. The basic fuel parameters important in gasifier design are particle size and shape, particle size distribution, char durability and fixed carbon content, ash fusion temperature, ash content, moisture content, heating value. So, particle size and shape. The size and shape of the fuel particles are important for determining the difficulty of moving and delivering the fuel, as well as the behavior of the fuel once it is in the gasifier. Good fuel hopper design calls for a cone angle that is double the dugout angle of repose, with an angle of repose over 45 degrees. The fuel may not flow even in a straight cylinder and will require either an inverted cone or some agitation. Smooth hopper walls are always desirable, obviously. Gasifiers frequently suffer from bridging and channeling of the fuel. The size and size distribution of the fuel determine the thickness of the gasification zone. The pressure drops through the bed and the minimum maximum hearth load for satisfactory operation. A uniform particle size helps overcome some problems. Improving the grate design, as well as added agitation or stirring, can go a long way to give trouble-free gasifier operation and to broaden the range of the fuel shapes suitable for gasification. At the same time, it is important to realize that excessive agitation results in excess carbon carryover, which in turn reduces the efficiency of the gasifier. In addition, carbon carryover reduces the oxygen-fuel ratio since the carbon requires more oxygen than the biomass for gasification. This in turn reduces the oxygen available for flaming pyrolysis and increases the rate of tar formation. So here's our table 3.6, ultimate analysis data for selected solid fuels and biomass materials, dry basis, wet percentage. That's interesting. Charcoal and char properties. Carbon is the name applied to a chemical element that occurs in dozens of physical forms, both pure, such as diamond and graphite, and impure, such as coke, charcoal, and soot. Charcoal refers to the 10% to 30% solid carbon product from biomass pyrolysis. Its composition can vary from 50% carbon to more than 80% carbon, depending upon the temperature and conditions of pyrolysis. Also, since it contains most of the original ash from the biomass, charcoal typically contains from 2% to 10% of mineral matter. Charcoal manufacture dates to prehistoric times and is a well-established industry today with standards for its various uses. Charcoal is simpler to gasify, and it is easier to clean up the gas for engine use than biomass gas is because of charcoal's low volatile content. At the beginning of World War II, most gasifiers used charcoal. However, charcoal manufacture wastes approximately 50% of the energy of biomass and usually requires hardwood biomass as a starting material. By the end of World War II, most gasifiers used wood instead of charcoal. Today, a large number of gasifiers built in the Philippines use charcoal, and charcoal is used in some other countries as well. It seems wise and probable that any long-term development of biomass gasification will ultimately use biomass again rather than charcoal. As charcoal is converted to gas in a gasifier, the ash content rises. We use the term char ash to describe the end product from the char gasification. Although the char ash is still black, it may contain up to 50% ash. The incoming oxygen air stream in the updraft gasifiers contacts the char ash at the grate and burns out the carbon, leaving a white ash. The principal problem in updraft gasifiers is to avoid ash slagging or melting, since it will plug the grate. In downdraft gasifiers, the char ash reacts with CO2 and H2O and is not contacted by oxygen. So the carbon is normally not completely consumed in a downdraft gasifier. The result is black char ash with 70 to 80% carbon. This carbon gives a good resistance to slagging. However, fuels with a high ash content can cause slagging in the area of the TURIs if they are used. Thus, the combustion and updraft gasifiers, the fuel passes through the stages: biomass, charcoal, char ash, ash, and slag. And in downdraft gasifiers, this process stops at char ash, right there. Charcoal durability depends on the resistance of the charcoal to powdering, duffing during transport, or char gasification. Ideally, the charcoal should maintain its size until the carbon reaches the end of the reduction zone. In practice, a wide range of char particles are produced in the reduction zone, and these can cause a plugging problem if they're not removed. Stirring and augering out char and ash are effective techniques for preventing this plugging problem. Figure 3.3 shows the char ash content as a function of particle size and the relation between carbon conversion and char size for the stratified bed gasifier. The fuel starts as biomass on the far right of the figure 3.3. Ash is 0.5% and carbon conversion is 0, of course. After flaming pyrolysis, half of the carbon has been converted, yet the resulting charcoal is only slightly smaller than its original size, 25 to 35% shrinkage. The char then undergoes gasification reactions with hot pyrolysis combustion products, which consume the carbon on both the surface and the interior of the particle. As interior carbon is consumed, the char shrinks, causing fractures, and the particle loses mechanical strength, causing crumbling. The small fragments are swept away by gas velocity. Returning to figure 3.3, we see a plateau after pyrolysis, and the char ash remains between 2% and 3% all the way down to under 1,000 nanometer particle size, indicating that the size particles has not engaged in much char gasification. Below 500 nanometers, we see a second plateau indicating the end of our char gasification and that there is little additional activity. It is clear that larger particles carry more unreacted carbon with them than do smaller particles. Therefore, the conversion efficiency will be maximized if removal of large char is kept to a minimum. The balance between conversion efficiency and the ash removal will be fuel specific. The final weight of the char ash residue is usually 2% to 10% of the biomass weight, depending on the char ash removal rate and char durability. However, the char ash residue is very low density and so may occupy up to 20% of the volume of the original biomass, depending upon the completeness of char gasification. Therefore, it's important to provide for adequate removal of this bulky material. Because charcoal often has a high value, gasifiers are sometimes operated to produce up to 10% charcoal by augering out charcoal at the end of the flaming combustion zone. This reduces the requirement for oxygen and increases gas quality to more than 6.8 megajoules per nanometer, but also increases tar content. However, no current commercial successful small-scale charcoal production in gasifiers is known to the authors. Charcoal is manufactured all over the world, and standards determine the quality and suitability for various uses. Recent tests at the Colorado School for Mines have tested char pellet strength at various stages of gasification. Next section, biomass, ash content, and effects. Fuels with a high ash content require much greater attention to great design, gas disengagement, and positive char ash removal. The slagging behavior of various crop residue woods, as shown in table 3.3.10, here we go. So the slagging behavior of various crop residues as wood is shown in table 3.10. Here we go. Biomass moisture content and effects. The fuel moisture content greatly affects both the operation of the gasifier and the quality of the product gas. The issues are addressed in the following sections. Biomass heating value. It can be seen in table 3.6 previously that there is a wide range of heating values for various biomass forms. A larger collection of heating values has recently been published showing variations for various biomass forms. However, most of the variation is due to the variability of MAF content and is reduced to an MAF basis. The variation is much less. Benefiction of biomass fuels. Chunky fuels, such as mill ends, chips, and corn cobs, which have at least one dimension larger than a few millimeters, can be used in fixed bed gasifiers without further size reduction, though they may require separation from fines and dirt. Bulky fuels such as logs, branches, and straw require chipping or chopping and possibly densification before use in most gasifiers. Densifying biomass fuels. Biomass fuels usually have bulk densities from 1/2 to 1/10 that of coal, as shown in Table 3.11, presenting a drawback for shipping, storage, and gasification. Biomass fuels also come in a wide range of sizes, many of which are not suitable for fixed bed gasification, such as sawdust, saunder dust, shredder fines, straw, and husks. However, biomass residues can be used in fixed bed gasifiers. They are first densified to suitably sized pellets or cubes using commercially available equipment, such as that shown in figure 3.4 up above. They make excellent gasifier fuels and allow the fuel to be stored in much higher densities. Densification typically consumes only 1 to 2% of the energy contained in the biomass for some residues. Drying may also be required additional energy, but drying simultaneously increases the fuel value of the biomass. Some biomass forms with high ash or dirt content are difficult to densify because they cause excessive wear on the dye. Wear of the dye. Also, densification is an additional expense, so its justification will depend on the comparison of the final fuel cost versus other alternatives. Drying biomass fuels. The moisture content of the biomass fuel affects the quality of the gas that will be produced. Water requires about 2,300 kilojoules to vaporize and 1,500 kilojoules to raise to 700 degrees centigrade during pyrolysis gasification. Therefore, this energy must be subtracted from the heat budget of the gasifier. Although it is typically possible to gasify moderately high moisture fuels in some gasifiers, fuel moisture reduces the quality of the gas as shown in figure 3.5. It also reduces the throughput of the gasifier and increases tar production. On the other hand, charcoal gasification is just the opposite. Inadequate moisture in inputs reduce the quality of the char gas. Figure 3.5 combines char gasification and wood gasification data to illustrate the impact of total water inputs on gas quality. Total water input includes fuel moisture, chemically bound water, and air blast humidity. We see in figure 3.5b that starting with dry gasification, gas heating values increased with increased moisture input up to a peak between 30 and 40% total moisture input. The gas heating value then declines with additional moisture input. Biomass can be considered as a source of water charcoal using the generic formula for biomass. So a generic formula for biomass is there. So the chemical moisture in bone dry biomass is MC. M sub C is equal to chemical moisture divided by the fuel weight, where M sub F is the fuel moisture percentage. We see in figure 3.5b that bone dry biomass corresponds to 47% total moisture input. The chemical moisture in bone dry biomass provides more moisture than is needed for peak heating value, and all fuel moisture reduces gas heating value. Biomass can contain more than 50% moisture, wet basis, when it is cut. It is generally desirable to dry biomass containing more than 25% moisture, wet basis, before gasification. Drying often can be accomplished using waste heat or solar energy. If the temperature of the drying air is too high, the outer surface of the chunk will become dry and begin to pyrolyze before the heat can reach the center. For efficient drying, hot air, which if cooled to 60 to 80 degrees centigrade would be moisture saturated, is preferred. The moisture slows feedstock drying as well as slowing surface pyrolysis. Thus, more air is required, improving the drying process. During operation of a gasifier and engine combination, 1-inch wood chips can be dried from 50% to 5% moisture content, with drying capacity to spare, using a 20-minute residence time with hot engine exhaust tempered with 90% recycle of dryer gases. Commercial dryers are available in many forms and sizes, and it is beyond the scope of this handbook to recommend such equipment for commercial scale operations. A simple batch dryer for drying small quantities of a commercial dryer is shown in 3.7. Biomass fuel emissions. The sulfur content of biomass fuels is usually very low compared with fossil fuels, as can be seen from the tables 3.6 and 3.8. Since sulfur oxides are corrosive, they make a major contribution to engine wear. The absence of sulfur in biomass fuels could allow a longer life for an engine operating on a producer gas rather than on petroleum fuels, providing that the producer gas is free of other contaminants. The nitrogen content of biomass fuels depends on the species of biomass used, as well as the harvest time, as shown in tables 3.9. Wood, dried stalks, hulls, and cobs have very low nitrogen content, while leaves, seeds, and bark have a higher nitrogen content depending upon the temperature of the gasification and combustion. This may significantly lower the nitrogen oxide emissions. From gasifier, I missed that. This may significantly lower the nitrogen oxide emissions from gasifier systems relative to those from fossil fuel systems. However, the final emissions depend specifically on the properties of the gasifier and the subsequent combustion of the gas, so that it is difficult to make a general statement about producer gas emissions. And that's our chapter 3. That's fuels. Next, we'll talk about principles of gasification. That was a very technical section. Probably need to go back over it a few times, but thank you so much for your attention, and we'll talk to you next time.